Hey guys, I wanted to give you a final lesson here on our topic in light. So far we've talked about the speed of light, we've talked about the history of light, and we talked about reflection in mirrors in the last lesson. And today I want to talk to you about refraction of light, which is a phenomenon that we talked about with other kinds of waves before, but we haven't really talked about how it applies to light specifically very much. So, refraction, remember, is bending of light as light passes from one medium to another medium. So, usually, we notice this the most with like light passing through glass or water or something like that. We notice that light sort of tends to distort. And this is the reason that our eyeglasses or contact lenses work correctly, or telescopes or cameras. We want to be able to bend light to form images. And you can use refraction to do it with a lens, just like you can use reflection to do it with a mirror. So, why does refraction happen? So, the reason is we talk about the speed of light being a constant, but really, when we talk about the speed of light c, we're talking about the speed of light in a vacuum. So, in a vacuum, light is traveling a lot faster than it would be through any other medium. So when it's traveling through water, it's actually traveling significantly slower than if it's traveling through a vacuum. It travels a little bit slower through air, but not much. Um, so why does it change speed, and how does this actually bend light? So something to understand is that if you have light just hitting something straight on, remember we talked about this being normal to the surface. If you have light just hitting something straight on, it's not going to change direction. It's just going to keep going straight, and then it's going to emerge through the other side. It's really only when you have light hitting at an angle does it change directions. And so we say this is normal to the surface here. But if we have it at some angle here, the rule for light is as it's slowing down, it always bends toward the normal. Okay, so it bends toward the normal. And as it's coming out of this substance, it would bend away from the normal. As it's speeding back up, it bends away from the normal. Well, why is this? So we talk about the incidence of the angle of incidence and the angle of refraction now between air and glass, or glass and air. And remember, it travels about the same light travels about the same speed in air as it does in a vacuum, almost as fast as it can go. But it travels much, much slower in glass or water or ice or diamond or something like that. So as it slows down, it wants to go toward the normal. So the angle of refraction is almost always going to be smaller than the angle of incidence as it slows down. Now the opposite is true. As light emerges from glass, it wants to bend away from the normal. As it speeds up, it wants to bend away from the normal. So what's actually happening is the wavelength gets smaller. So as the light hits the new medium, the wavelength shrinks, and it always shrinks on the first side that hits it, and so that's why it bends into whatever it's striking that slows it down. Okay, so it's going to bend on the near side first. I had a physics instructor explain this in terms of a shopping cart. So imagine you have a shopping cart, and I think I've talked about this before. Imagine you had a shopping cart on just a smooth surface, and then you had a rough surface. Now, if you pushed the shopping cart such that it was going straight in to the other surface, it would slow down when it hit the rough surface, but it would probably keep going in a straight line. But if I have it at an angle, if I push the shopping cart at an angle, what would happen is this first wheel would catch the rough surface and it would want to slow down. And what would happen is it would kind of wrench the shopping cart around and sort of bend it into it. I don't have a shopping cart in front of me to demonstrate this, but I think that you would agree that it's more likely to bounce or to continue into it at a shallower angle than it is to change directions. Think about how counterintuitive that would be if it hit this and then continued at a shallower angle along it. I think that that's very unlikely. It always wants to bend into the medium when it slows down. Okay, so the degree to which it bends in is called the index of refraction. But this is different for different colors. So we've seen this like sort of Pink Floyd picture before of light going through a prism. So Isaac Newton discovered that white light was a mix of other colors. So we talk about the Roy G. Biv, red, orange, yellow, green, blue, and violet. The reason that it separates is that we said that the wavelength is shortening. In the same area, there are a lot more violet wavelengths than red wavelengths. So if I have 1.5 times as many violet wavelengths in the same area, the violet wavelengths are going to slow down or are going to shorten a lot more significantly than the red ones. So as a result, violet always slows down, or blue always slows down more than red light. Red light is the least affected by the refraction. Okay, this is also why we see a rainbow. Okay, so why do we see rainbows in a light? Why do we see rainbows from the sunlight? Notice how the sun is always behind you when you see a rainbow. What happens is you're actually seeing light passing through and reflecting off the back of a water drop. But since violet light refracts more than red light, you always see, think about the arrangement of the rainbow the next time you look at it, what it's going to look like. So what you're seeing is sort of a virtual image of a rainbow with one color on the inside and one color on the outside because of the light reflecting off the back of the water drop. Okay? So the degree to which it refracts is called the index of refraction. And the index of refraction is just a measure of how much light slows down. So we can think about it as if the speed of light in a vacuum was the same as the speed of light through water or glass, the index of refraction would just be 1. It would be traveling the same speed in both media. Okay? But if it slows down to half the speed, if the velocity in water or whatever was half the speed of light, then the speed of light divided by half of its speed would be 2. So the index of refraction would be 2 if it slowed down by half as much. So the bigger n gets the index of refraction, the more light is slowing down. So what's a common index of refraction? Well, for water, one that we can always remember is almost exactly 1 1/3. So light travels about 1/3 slower through water as it does in air. There's many, many, many different kinds of glass and plastics and things like that that all have different indices of refraction. So crown glass is depending on how the glass is made, if it's tempered or whatever. Some are going to refract light more than others, but glass actually is usually more of an index of refraction than water. Here's something to consider. Diamond has a very high index of refraction, almost 2.5. That means the light is traveling almost 2.5 times slower, so about 40% of its speed through diamond as it is in air or in a vacuum. Now you say, Mr. Kuiper, you just said that all light is traveling, or all light refracts at different degrees. So normally when we talk about this, we're talking about a specific color. And so this is 589 nanometers. That would be like yellow or orange light. So like kind of in the middle of the spectrum, how much that is. So blue light would have a higher index of refraction than red light. But we usually just measure one. Usually it's yellow light. Okay, so this also changes how things appear in water or glass. So obviously, remember, your eye can only perceive light as coming from a straight line source. So if light is speeding up as it exits the water, it's going to bend away from the normal. Okay, but your eye is always going to perceive something as being coming from a straight line. So things always appear to be shallower in water than they really are. So when you reach your hand into water, or when the cat reaches for the fish is always going to be a little bit deeper than it appears to be. Same as opposite. The same is true. This is what I was trying to explain with the pool. The cat is going to appear to the fish as being higher up than it really is. Okay? The cat is actually closer to the surface than the fish thinks that it is because it can't tell that light is actually bending. So things change positions. Another thing that the index of refraction is useful for is identifying objects. Okay? So one of the reasons diamonds look so much different from anything else is the way that they sparkle. Since they have, sorry, my daughter's trying to get into my office here. Since they have so much of a higher index of refraction, what happens is they reflect light internally more, and that's why they appear to sparkle so much. So you may have purchased jewelry or someone given you jewelry that has what's called a CZ stone, which means cubic zirconium, which is actually a pretty nice looking stone. It's a good imitation of a diamond. But one easy way to tell that it's not a diamond is by how it refracts the light. If you held the cubic zirconium over a straight line, you would be able to tell it only bends it a little bit, whereas a diamond completely obscures the line because it refracts it so much. Here's another example. You can tell if you put two stones on a white background which one's the diamond. The diamond refracts the light so much that it completely obscures the background behind it, whereas the imitation diamond, I think this one has said it was moissanite, looks more like glass because you can kind of see through it without it refracting quite as much. So that's a whole area of forensics, is identifying plastics and glasses by their index of refraction. I had one other thing to mention. So lenses can be constructed using the same principles of mirrors to form images. And again, you have two different kinds of lenses, just like you have two different kinds of mirrors. Remember, you had a convex mirror that always produced the same kind of image. Remember, Mr. Boyer's head got smaller every time. And then you had concave mirrors, which could flip over an image, and they sort of could magnify an image as well. Well, lenses use the same principles, but because light is actually passing through the lens rather than reflecting off of it, the concave-convex is opposite. A convex mirror is always a converging lens, or a convex lens is always converging, meaning this is the kind of lens that can flip an image over, whereas if it was a mirror of this shape, it would never be flipped over. It would always just be reduced. Most people who wear glasses are nearsighted, and you'll notice, so if you were to hold your lenses up to a bright light, I think I did this with a projector, it always spreads the image out. Okay, so this is what we'd call a diverging lens. This would be the same as the sort of the rear view mirror effect, where the image is always upright, but it's always a little bit smaller. Okay, if you're farsighted, you have lenses that look like this, but those always tend to magnify your eyes. Okay, so if you ever notice somebody is farsighted, their eyes look like magnifying glasses. They look like they have huge eyes underneath them sometimes, depending on how strong of a prescription it is. But the same principles of image formation and ray tracing that we did in the last lesson hold true for lenses. It just depends on, there's an added feature in here of what the material is made of that sort of exacerbates or I don't want to say magnifies it. It makes a more extreme angle depending on what the material is made of. Okay, so but the whole idea of ray tracing and image formation holds true for lenses as well. Okay, so I'll have a little review for this, and this will be the last lesson in physics. So it's been a great year, and I wish I could show you some of these examples in person and get a chance to wish you all good luck in person. So thanks for a great class, everybody.